I want to welcome on stage Jean-Claude. I want to also use this opportunity that we've always been saying when we connect to any online system, like, can you hear me? Can I hear you? Can you hear me? Yeah, perfect.
I hear you.
All right. Jean-Claude is from CCCS, which is the Canadian Cybersecurity Center for Cybersecurity. And I've been working with Canadians for at least 2 years now doing threat hunting operations, and I'm very glad to have CCCS representative here. So Jean-Claude, without further ado, you're up next. There you go.
Yep. Thank you, and good afternoon, everyone. I'm Jean-Claude Côté. I have 30 years of software development experience, and the last 10 years have been focused more on big data. I'm a principal engineer at CCCS, Canadian Center for Cybersecurity. So we're the Canadian CERT, and we're part of the Communication Security Establishment. Today, I'll be presenting a research initiative to run streaming Sigma detections at scale. So this is kind of the way it's going to go. So do a brief overview of what CCCS does, a brief overview of our data flow, the project objective for this initiative, and go into details how we did this, and a small conclusion. So the role of CCCS as a CERT is to inform and protect the Canadian. We develop tools and techniques. We have quite a software development focused shop, as well as all that goes with it. So we help and defend the Canadian networks. We believe security is a team sport, and so that's why we share our tools and our techniques, and we make it a priority to contribute to open source. And we share our information via blogs as well. So this is a high-level overview of how our data is flowing through our system. At the top, we have a streaming, and at the bottom, batching. So we collect data from all sorts of sources, from endpoints, clouds, network gateways, or just logs in general. This data will come in in all sorts of file formats, or all sorts of shapes as well. And so we have a phase of normalizing the data to make it look all the same, labeling it, and possibly enriching it with some more information. Then it transitions into more of a data engineering phase, where we're going to start modeling this data into fact tables, dimension, possibly daily summaries, and so forth. And for this, we use a tool called DBT. So from these sources, we run analytics, so either in batch or in the streaming. And then it produces alerts that analysts will, triage team will look at. Today, I'll be focusing on the streaming aspect, so this red box here. So what were the objectives for this initiative? So first of all, it was to simplify the creation of detection. So we based ourselves on Sigma. The other thing was to reduce the time to action compromise. So we believe doing this in a streaming fashion will achieve this. We wanted to improve our scalability. We constantly get more and more data. I think a lot of people are live this experience. It just keeps growing, and so the system has to be able to scale. And the other thing is to reduce our cost, particularly for storage. So last year, we came and presented to you assembly line, which is a production system, well established, and it's an open source. This is not the same. This is a research initiative, so we're showing you how we're kind of elaborating a project, and so this is kind of from the ground up. So it's a proof of concept that we have so far. We're transitioning this into production now, so it's the rubber meets the road. You know, we'll see how it fares, and then we'll have more realistic or real metrics and measures. So it's coming soon. So this research initiative is based on these technologies. So Sigma, to describe the detection logic, we're already invested quite heavily into Iceberg. It's a table format. I'll explain a bit more what that is. We use this for storage, and we're starting now to use it as a queuing system as well. Our main workhorse for processing is Spark. And so to do streaming, we're going to use Spark streaming because we're familiar with Spark, and it also makes things more uniform. So what is Iceberg? So Iceberg is a table format. In the world of big data, data resides on disk and files. It's very simple, as you see in this little diagram on the right here. The idea of a table format is to abstract the files into a table, and to work around the limitation of the file system, like listing files all over the place takes time. And so the idea is to centralize keeping track of files into this metadata here, and to give you a view of your data more as a table. There's many benefits to doing this. So for example, as people add files to this, they will do a commit, which will go in the metadata, and only after a commit does a client see the newly added file. So it makes things more transactional. It also keeps a history of all the commits, a bit like Git, so you can time travel inside your table. So you can view this, the table format, as analogous to what a file format is. So for example, in big data, there's a Parquet file format, which describes the structure inside a file. This kind of describes the structure of files on disk. Iceberg is not the only table format. There's a few more. Databricks, Delta Lake's probably the most recognized. But all these table formats, they just rely on simple disk. And so that's why they're a cheap alternative. Now, Iceberg has a very nice thing about it is that you can access your data in kind of two ways. So on the right here, I have a classic view of it where you would have a table name, and remember that this abstracts all the files and where they are and so forth. So you just speak in terms of tables. And it will translate in Spark what does that mean, like which file to go scan. So this is a traditional view of it. But this metadata also enables streaming, in the sense that now that when you use Spark streaming, what it will want to do is ask your source, what's new since the last time I took data from you? And because Iceberg keeps a history of all the commits, it knows all the files that were added to the table, and so it can quickly tell you that there's 2 commits that are new. These are the files that have been attached. And so there's kind of 2 access patterns that it provides. And again, all the data is on disk, so it's a cheap way to store your data, but also a cheap way to stream your data. So typically, or the most known way to stream data is to put it in Kafka queue. This is great, but running a Kafka cluster, you need compute, first of all, and if you're going to run your own Kafka, you probably need a team to support this system. you can go the SaaS way. So on Azure, it would be called event hubs. So you don't do anything, they do it for you, but it's even more expensive than running your own compute. In Iceberg, all you do is rely on the blob storage SaaS, which is relatively cheap compared to these two options. The other benefit of Iceberg is, contrary to these two approach, 1 and 2, you're not limited in size of your messages like they are. The downside is that since these are files on disk, you can't expect super low latency like Kafka can do, in tens of milliseconds. You're now more in tens of seconds. But we believe that for a large majority of our use case, this is sufficient latency. And for the ones that we want a super low latency, then we will look at the Kafka or Event Hub solution. But we'll address the general case using Iceberg. So this is done quite frequently in big data. There's a great QCon talk that was done by Apple recently that goes into great details of this approach. Okay, so we want to standardize as an organization on Sigma. Sigma is usually compiled into queries that are run in batch. We want to do a little twist on that and compile them so they're suited for streaming. So what's Sigma? So I like this quote from Sigma HQ because it captures all of it in a nutshell. So Sigma is for log files, what Snort is for network traffic, and Yara is for files. So the idea is to have a generic description of your detection logic, which is abstract. And then you apply an abstract, and you can't execute it. It's just a description. Then you have compilers that will transform this abstract description into specific concrete queries or searches for, say, for Elasticsearch, Splunk, for SQL, for example, which then can be executed. So another part of it is the fields that are or nouns or described in Sigma, they need to be mapped onto your specific telemetry. And so this is also part of Sigma, is this mapping of abstract fields to concrete ones. So the benefits we see, well, it's an open standard, so we want to just adopt standards. It's portable, so when you write a rule, in theory, anybody can run it on their favorite platform. And having a common vocabulary, like I was saying, the nouns, the fields that are common, but you can map to your specific, and the verbs too, like this field would contain a certain string, or ends with a certain thing. These verbs are also common. So this promotes sharing because I can explain to you quite clearly what the intent of the detection is, and you can then map it onto your specific system. So we're already invested, like I was saying, into Spark. We also adopted Trino. We have Oracle and Azure Log Analytic as well. These engines all support SQL, and we believe that SQL is a great language in the sense that it's portable across engines, and so the skills you will learn on one, you can transition to another tool. So we're kind of encouraging SQL for this reason. And so we took the existing PySigma SQL backend, and we're going to extend it as we go and see fit with our needs, and then we'll contribute back to the open source. And so this is kind of the crux of it, of what we want to do. On the left here, I have a Sigma rule. So it's a Yara file. The heart of it is this section here where you have a detection. So within a detection, there's always a condition that's composed of various filters. So now you can name these filter whatever you want. Often people name it filter, but this could be any name and selection as well. The idea is that these are Boolean tests. And so, for example, here this field contains one of those, or this field is equal to post. And so if we translate this to SQL and compile it, you see here the mappings, you see filter and what expression it is, and notice that filter is a Boolean. Same here. And then the final condition is putting all this together. And here's the result of the rule. So let's say you name this rule web shell George, and it's a Boolean. You notice as well as you that this is typically how Sigma is compiled, but ideally we would like to run multiple Sigma rules simultaneously. Since we're going to go through the data, might as well test all the rules at the same time. Here it introduces fields. As we add more rules, we'll introduce more fields, so that the schema is going to change as we go. So we want to address that, and this is how we're proposing to address that. So when I speak of SQL, in this world of Trino and Spark, this is now called like modern SQL. These engines are not limited to simple scalar value. They support structure or objects, arrays, and maps. So it's equivalent to working with JSON rather than CSV files. And here I have a little example. So name struct is a way to build an object, so a user object. I can make an array, I can make a map, and then when you execute this, you get the result that's one row, but you notice that user is actually an object with a name and an age. This guy is a list, and this guy is a map. Now, this table here, this result, I can store in Iceberg. Iceberg supports all this complex structure, and you can read from it. So it's really a world where SQL, it's not traditional SQL. It's structured or with data structure. But we can use this to our advantage in running multiple Sigma rules in a single pass. The way we are proposing to organize our detections is to use a map structure, put the rule name here, and all the detection logic here, so that in the end, when we run it, we'll get the rule name, and if it passes or fails. This is a great thing because now our result table that's down here, it has a fixed schema. As we add more rows to it, they'll just be inserted in this map, but the schema of the table will not change. And the reason why we want to do a single pass is because we're going to bring this data in memory to perform tests on it. Might as well do all the tests possible in one go. Okay, so now there's kind of two ways to run this. Either we run it in batch or in stream, so I'll contrast the two. So this is a typical setup to run Sigma in batch. You'll have your engine here running the detection, the queries, going to your source of data. So probably you've ingested it and indexed it for searches. But you have to keep your last trigger, like what's the last point in time that you worked from. You'll have a scheduler that triggers this constantly, say every 10 minutes. But it's on you to maintain your point in time or your checkpoints of where you were at in the table. Now, when you look at the Spark streaming, they kind of have a similar model. Within Spark streaming, they use what they call micro batch. So basically, they do little batches all the time on a trigger, and they will checkpoint where they were in your source table, like here. And remember that here on the left, we're talking iceberg, so it has all this commit history. It can quickly know which snapshot it is. Then Spark commits which snapshot you're at, and it does all this in fault resilient way, meaning it stores it on a data lake, which is also fault tolerant, in case that the machine you're on would simply die or you lose it. And the other thing is that Spark, well, the API for batch and stream and Spark are the same, and so it's very easy to switch from one to the other. So it's a matter of saying read or read stream, but after that, it's very similar. So you can apply the same logic to either mode. Okay, so far we saw discrete detection, so detection on a particular message or row. This is kind of the simple case, and Spark does that very well. But there are the rules that require aggregation, so not just a single point, but a few points within a window. So for example, you could count the number of failed login attempts in a window of 3 hours, let's say. So here's an example of a Sigma rule that does this. Okay, so like before, there's a detection, a condition, and selection is one of the filters. But now it introduces a time frame, so a window, on which you'll run an aggregation function. And so here is summing question length of a DNS record, group by source IP and greater than this. So it's again a Boolean test, but now it's using many data points in the stream. And here's another example. Again, same things, the filters and whatnot, and the time frame, and now it's doing a count, by source address greater than 200. Now, let's say we want to run this type of thing, aggregation on a batch mode. So same setup as before, but notice now that say we want to check for 20 logins within 3-hour window. So every 10 minutes, we're going to wake up and go look at this table, but we're going to be reprocessing a 3-hour window when we pretty much covered it the first time. And so we're going repeatedly over our window, constantly. And it gets worse as you want to bring your trigger down and do it more frequently. Now you're going even more over your window. If we look at how Spark does this in the streaming mode, introduce stateful operation. So in memory, it's going to keep the state of these aggregations, so summing and counting. And as data is coming through Spark, it will increment these counters in memory and keep the state. So again, because of fault tolerance, let's say the machine dies, when it checkpoints where it is in the stream, it also is going to checkpoint the state that it has in memory to disk in case of failure. And so if it ever breaks down and gets restarted elsewhere, it's going to pick up its old state and continue from where it left off. And notice, this means that we're reading the data only once, like we're not going over and over this time window. It incrementally adjusts our counters. This works really well in Spark because it keeps in memory, it's very light. And so now we're going to look at another variant. So we saw discrete aggregation. Those are run very well. This one poses more challenges. So detection that required joins. And this is typically when you need to join with the past event that you've seen go by. And I'll give some examples. So here's a Sigma rule. It's from a create process, so starting process events. You'll notice that it talks about image, which is about the current log or current message, but also refers to a parent command line, which it assumes that you have, because it just uses it in its detection here. But this is not always the case. And for example, in this telemetry of Windows event, we see that we have information about the process, so the process ID, the process name, and the process command line. And it gives you information about your parent and who started you. So this is the parent ID and the parent process name, but it doesn't give you the process command line. And so to address these scenarios, these cases, you need to do a join, or the Sigma rule assumes a join was performed. So luckily, Spark even supports joining two streams of data, and so it's built in already. The way this works is you'll read once and read another time and perform a join on it. You ask Spark to do this. At the bottom, we don't need really to cache anything. As things go by, we want the join to look into this window here of past messages and trying to find a match so it can bring here the current event and its parent attributes. And so now we can apply the final Sigma rule. This, of course, requires memory to hold all these past events here. And so you want to be smart about how you go and keep what you put there. So, and notice too that in our case here, let's say we talk about start process, the stream here and the stream here are actually the same source. It's the same logs. Okay, so that's like, it's called a self join. So this is just like focusing on the join and what it needs. So at the bottom, you have the current event, but particularly the parent PID. So it lets you join onto this past events. And so you need the parent PID here. You'll want to keep in this window only the parents that might contribute to detection. So only the ones that have a certain command line, for example. The other ones, we don't really care. Like they won't contribute to detection, so we can just filter them out from this window and reduce the size of what's there. Another thing you might observe is that I don't really need to keep the parent command line there. Strictly speaking, I need a Boolean value for the condition to evaluate to true and give me, yes, this match. And so we can further bring this down by simply keeping just Boolean features or tags. So they're the result of applying the filters in Sigma. You can even reduce your PID. Let's say your PID's a string, a UID. You might say, well, I'm just going to make a hash of it and just keep my IDs as numbers so that to reduce the size. So we've evaluated this thoroughly in Spark to see its performance, and using a large machine of 16 CPUs, 64 gigs of RAM, you can pump 2,500 messages a second and keep 160 million Boolean tests in here. This is good. It works fairly well. It's as much as Spark can do, and as much as you can push it. But we would like to improve on this, because this window, the more we can put stuff on, the longer in time we can look back. And so it's kind of important to have a good look back, because start process might be the second later, the minute later, but could be hours later. And so we want to improve on this stream join. So I mentioned already, alluded to, it's reading the stream twice right now. could we read it once? The memory, the things that we're keeping, we did our best with stream join. Could we reduce this further so that we get a longer look back in time? And so in Spark, you can write your own functions. So typically, well, in many places, Spark has built-in things, but there's always a hook to write your own. Okay, so so we looked at writing our own function to do the join. But yeah, and so when you look at it this way, you can tell yourself, well, what am I really doing when I'm joining and I'm pulling stuff from the top window? I'm really getting the results of the tags, of the features evaluated, the Boolean test for a given parent. And so you can see that as what you need is a map, and you can, as data is coming in and you see some kind of parents of interest, like a command line that matches a parent, you can put this in your map, and later on when you see a child process from it, you can use this parent PID and pull this out and then put the two together and you output the two and you can do the final evaluation. So really you did basically what the join was doing before. That's just using a map and a custom function. When you do so, one of the great benefit is now that you read your stream once and you stuff things in there and pull them down when you need them. And so you save on reading. You just do it once. Building your own custom function in Spark, again, it's very nice because you still leverage Spark fully. It's going to do the checkpointing. It's going to even store your state here for you and recover it in case of failure. So really, you're just focusing on writing the logic that you want to do on your stream. So doing a hash set is great. It works well. But does not really save memory compared to what the stream join does in Spark. And so we've replaced this map, this hash set, with Bloom filters. So now these keys, that we used to do for lookup, they're stored in here, but only their fingerprints. And so, like before, we were talking about the keys just being even a number. By using a Bloom, each key can now take just a few bits rather than 32 bits or 64 bits, which was the best we could do. Now we're down to a few bits. And again, we're reading the stream only once. And so when we applied this, the custom function and having a state of Bloom filters, and we compare with the stream join, we get over 100 times more capacity in storing Boolean tests. We also process 4 times the rate of messages as compared to the stream join. But of course, using Bloom filters, the downside is now it's introduced possible false positive. So this is kind of how Bloom filters work. At the top here, you have a key, so X, and the way a Bloom works is going to hash this. So X could be a number, it could be a long string. We're just going to hash it, and it's going to give us a position in a bit array that we should turn on. So, and we do this 3 times. So here and there. And notice if I take another key, it might hash to the same spot. So this is already on. So we save on space like it was already there. And when we test, we come here and we hash this 3 position and we check, is it on? Is it on? Oh, it's not. So if it's not on, so we've never seen W ever. And we can be sure because this was never turned on. And so false negatives are not possible. And that's good because we don't want to miss any alerts or any detection. But W could hash to 3 bits that are not all given by the same key. So it just happens that the keys there touch those, but we don't know that only one key did that. And so false positive, that's possible. And this website is a Bloom filter calculator, and you can see as you insert keys in your structure, the probability of false positive, it goes up and at some point drastically. And it's not possible to turn off or remove keys from it because they might share bits. And so once you put stuff in there, it's done. Like you can't take anything away. And so there's a great paper from Redis Lab about addressing this, like addressing Bloom filters over time and how you can make a Bloom filter that keeps going, because like as mentioned, they will fill up. And the simplest approach in the paper is simply to make a ring of Bloom. So you take your big Bloom, you split it in a few segments, let's say 10 segments, and then you rotate through them. And so you'll have, say, an active Bloom where you're gonna do all your puts, but when you do a get, you're gonna check for the old ones, all of them. When the active Bloom fills up, you're gonna look at your oldest Bloom, drop it, create a new one, and then make this the active. And so this will let you rotate through these segments, and make it so that your Bloom that never fills up. One of the benefits of doing this too in Spark is that we can tweak Spark so that when it stores or checkpoints the state, it only stores this guy, because the other ones are not changing ever. Because once we finish putting in this, we're never gonna modify it. So once they're loaded in memory, we can just keep them there and only save this guy, which is the one we know is changing. So we've named our custom function a flux capacitor. Like a electrical capacitor, the function, it keeps Boolean test as it goes. And so it's kind of accumulating charges. Also, this function enables us to kind of time travel and look at past observations. And so it's kind of a time travel function at the same time. So we named it the flux capacitor. Using it, we were able to achieve the goals of reading the stream once and using less memory. And conceptually, this is very simple. It's all we're doing is caching observation with a name. But this approach, this simple concept, it can address many use cases. So we saw how we can address a parent use case, but we can also address a parent of parents, and so go further back into the hierarchy of processes, and so call this the ancestor. Note this would normally require joins of joins of joins. Another thing it can do is address this temporal proximity, which is a sigma 2 specification, which I'm going to get into. So ancestor, okay, so this is a bit like describing the mechanics, how the function operates. And so on the left here, we have telemetry coming in with the time going down. And on the right is the cache. And so on the first row, we come here, we have a parent command line that matches. So this could be a parent of interest that later on a child will want to join with and make a detection. And so we want to keep this test and remember it. And so what we do here is do a put. We put 300 as the PID and the name of the filter right here, or the tag, and we kind of compose a key that we're going to set in the Bloom. And remember, this is just turning on a few bits in there. Then on the second row, we get no match of anything, but we nonetheless gonna go check inside our Bloom if we have a parent of interest lying around in there. So we're gonna look up 300, parent command line, and sure enough, it's turned on. So we're gonna pull this down on the row here and flip this Boolean to true, and also push it back under our PID, so that we get the effect of ancestor and pushing the tags down multiple levels of hierarchy. And so we store it like that. On the third row, we come here, and now this child happened to match. Okay, parent did not match, but did we have something cache in the flux capacitor? We go check, and sure enough. And now we have both of them on the row. They're both true. The final condition will evaluate to true, and we've achieved a join, but over multiple levels possibly, which is something very difficult to do with the purely join approach.
Jean-Claude, also one thing from our side, we have about 5 minutes left. So if you have like the key aspect that you want to still go, because up to now you've been giving a lot of valuable information, but last part, thank you.
So this is temporal proximity. It's a Sigma 2 spec. The idea is to have observation in a window of time. So I won't elaborate. This too here we can achieve with the flux capacitor. It's just a matter of when to put stuff and when to pull them out of the cache. But the key takeaway here is that it's a simple concept, but depending on how you use it, you can implement different use cases. And possibly there's more use cases that we have not yet discovered. So I showed how this is all great, but it does introduce false positive. There's no false negative, so we're not missing alerts, but we are potentially polluting our triage analyst with a lot of false alerts. So we want to make true alerts. And so this is kind of the final layout of the whole thing. Here we have a Spark job, a streaming Spark job that does detection. So we'll do a pattern matching of what's coming in and stuff things in the flux capacitor for its cache. So we basically perform the join. In 3 here, we're going to store everything we've seen here and organize it so we can search in it well. In 4 here, we're going to publish the ones that are suspected anomalies, but we're not 100% sure. And in 5, we have a second job that this job is to validate everything. But of course, it's reading suspected anomalies, so a very low volume now. It goes back into the telemetry, retrieves the actual log lines that are implicated in a certain detection and replays it, so making sure it's a true detection. And now we have the luxury of not using blooms. We can use a hash set, so we're sure for sure that it does match. And a bonus, we have all the evidence, all the telemetry that's involved in the alert. And so we can give that to triage analysts, and you have the proof, and they can double check that everything is correct. So having false positive is not great, but in the end, it doesn't really affect things because we would need the pieces of evidence anyways. And so it's not much added. So Bloom filters is just a form of data sketching. There are many more probabilistic algorithms addressing different use cases. So for example, the unique users, histograms, and most frequent sets There's quite a lot. So Lee Rhodes is a distinguished scientist at Yahoo, and Yahoo have open sourced the data sketch libraries, and so there's tons of opportunities there. We haven't scratched the surface. So that's it.
All right. Thank you. That was a very, very interesting and dense presentation. Thank you so much.
Yes.
Well, let's give an applause. I hope you can hear it. Although we're a little bit over time, I want to still take questions from the audience if there's any. All right. Well, there is no questions from the audience. However, I always come with a question. So,
okay.
You mentioned that this is currently a research, right? It's not released publicly as the other platform, the assembly line.
Assembly line, yes.
So it's not yet released. It's still in a development phase. Is that correct?
Yeah. Here's our the Git repo of our proof of concept. So we're kind of developing it openly, but
oh, I see.
It's not production, like, you know.
Oh, so did you have a chance to test it in the real cases, like threat hunting operations, or working with huge volumes?
Exactly where we're at. We're at transitioning this on real telemetry, you know, real detections, and see if it fares better than what we not trained it on, but you know, when we make a proof of concept, we make assumptions, and so now we're going to have the real things and see how viable it is. Does it fare okay?
So the actual testing has not yet begun. So you're planning to launch it in a threat hunting or any other operation that you're going to conduct, right?
Yeah. So we're gonna just put it on our telemetry and see how it fares.
So why I'm just mentioning the word of threat hunting over and over again. First of all, because we, together with the Canadians, we've been engaged in conducting threat hunting operations here in Latvia. And this is where we typically get a lot of log files, for sure. This is when we are onboarding a particular organization. This means we deploy the WinLog or syslog just to start collecting data. So this is like some historical data, give or take. There's a stream of ongoing data, and then the threat hunting analysts are going on the systems extracting the data. So there are like multiple sources being fed, and there might be like 15,000 hosts, and they all simultaneously report on a single query done by the threat hunting operator. How would you envision, would this system be able to digest such huge volumes of data coming in simultaneously as a spike and process? I suppose most likely, but maybe latency or time?
Yeah, most likely, because the idea is to make it highly scalable. And so like what I've shown there was with one machine doing detection. But if the volumes are dictate that it needs more, you can replicate the number of machines. And so then it really just becomes of how many compute do you want to put on the problem. But of course, you know, you want to control costs and say, well, I made the detection as efficient as I can. Now I'm forced to just put money at it and compute. But that's the idea, is to squeeze the lemon as much as possible. And then when the software side is, you know, as best we can, then you just put raw compute and power and just ask Spark to scale it.
All right. Thank you so much for the presentation. And I didn't start my my welcome with saying good morning, because you've been awake awake really early. So I hope your day is going well. And so thank you for joining us so early.
No problem. It's my pleasure.
All right. Bye-bye. Take care.
Bye-bye. Thank you.